and just witness that it's a craziness in Paris. Everybody, you know, lily of the valley, right? This little white flower.
Mm-hmm. Yeah.
I forgot the German. Well, I mean, you probably. What is my Glocken in German? Anyway, so that's a tradition that 1st of May everybody wears or gives us a gift this this flower. So it's called Muguet.
So what is the name of today, Igor? What is it? What is today, Igor? What's the name?
Today's second, right? The second is nothing as far as I know. Well,
okay. All right. So I think unfortunately we need to start now. It's according to my, you know, better than the atomic clock, which is my iPhone. We're on time now. So I would like to thank everybody once again to join us the online SPICE-SPIN+X seminar. It's actually one talk this month. Sorry, but we've been in recess a little bit, writing some proposals. But welcome again. I'm Jairo Sinova, and together with Libes Meikkiala and Jack Wittmann and Karen Eversociety at Duisburg, here in SPICE, we organize these seminars in collaboration with the SPIN+X Collaborative Research Center, run by Martina Schliemann and Burkhard Hillebrands in Kaiserslautern and Matthias Chloe in Mainz. As you guys know, this is a Zoom seminar, so you will hear the speaker, and then you can ask your questions or put them in the chat or in the Q&A, and I will then dictate later who gets first and then promote you to panelists to ask directly to the speaker. Unfortunately, this month is also full of workshops that we don't usually do the seminars at the same time, but you will be able to also see them online pretty soon, also in the altermagnetism workshop that we have next week. And maybe some of the other workshops in the spectral electronics in Japan and quantum spectronics, some of them in SPICE. Today's speaker, is a pleasure to welcome Silvia Picozzi. She had been to SPICE before here in Mainz, but now is the first time online. She's the director of research at Consiglio Nazionale della Ricerca. Sorry, I'm butchering the Italian. Very sorry about this. So she's very well known in our field, particularly materials modeling, to functional theory, functional materials, both ferromagnetic, ferroelectrics, and multiferroics, and particularly materials with the strongest spin-orbit coupling topological effects of matter. She was awarded 2019 the Fellow of American Physical Society, and also obtained an ERC grant a few years ago. So with that, I'm going to stop sharing, and I'm going to ask Silvia to please go ahead and start your presentation.
Yeah, can you see the screen?
Yeah.
Okay.
And, go ahead and start, and I'll mute myself here and I'll give you the floor.
Yeah.
We're looking forward to it.
Yeah, so thanks so much, Jairo, for the kind invitation. It's really a pleasure for me to give this seminar today. And so this is basically the outline of the talk. As the title says, I will basically discuss spin-orbit coupling by giving first a very brief introduction and then showing mainly what spin-orbit can lead to into the magnets, but also I'll briefly touch on the connection between spin-orbit and ferroelectricity in the beginning of the talk. Okay, so let me also introduce who I am. So I work in Italy, as my accent would probably tell you. So I work in between the Apennines and the Adriatic Sea in a small city called Chieti, and I lead a small group. So you see here Paolo Barone and Danila Moroso, who are the main players of the results that I will show you today. And so I, of course, like to thank them for their job. And so, as Jairo said, I work on several kinds of materials, maybe oxides, but also, organics and interfaces. And then a few years ago, I moved to 2D magnets. And as Jairo again said, I'm basically a density functional theorist. So you will see a lot of band structure in the talk. And so we usually do first principle calculation, but also we benefit a lot from complementary tools by means of, for example, symmetry analysis or model Hamiltonian. So our, let's say, expertise is basically understanding microscopic mechanisms that lie behind our band structure. So we really like to focus on the mechanism driving some phenomena. Of course, if we understand the mechanism, then we can optimize and do eventually some materials design. Yeah, so our expertise since like a couple of decades is basically on intertwined phenomena. So for a long time, I've studied the connection between ferroelectricity and ferromagnetism by addressing a class of material called multiferroics. And then I moved to the connection between ferroelectricity and spin-orbit coupling by proposing a class of material called Rashba ferroelectrics. And then more recently, I moved to the connection between magnetism and topology by addressing skyrmions. And so today I'll briefly touch the three topics. So, okay, very general, what is spin-orbit coupling? So spin-orbit coupling is a relativistic interaction, which basically connects the spin and orbital angular momentum. And it's usually in most of the material we study, neglecting plutonium and uranium, it's usually a small interaction, small compared to the other energy scale at play in, for example, bandwidth or hybridization. Spin orbit is much smaller, so it's a couple of orders of magnitude smaller, but still it can give rise to a wide variety of phenomena. And it's relevant both in non-magnetic solid, so all the topological type that we have in the last, I don't know, decade or so, is actually strongly rooted in spin orbit, and also other peculiar band structure effect that you have, such as Rashba or Bresselhaus effect or spin valley coupling. They are actually based on the spin orbit interaction. And of course, it's relevant in magnetic solid. And probably the most known manifestation of spin orbit coupling is magnetic anisotropy, which is also tremendously important for all the application based on magnetism that we all use. But it's also at the root of more exotic interaction, which I will discuss today, such as stereochimeria and anisotropic exchange. Yeah, so before I go to the 2D magnets, and since it has been this occasion of Rashba 95th birthday, and I worked for a long time on Rashba, I thought it was useful to discuss a bit, just spend a couple of slides on the Rashba physics and our, let's say, contribution to the Rashba physics by means of the connection to ferroelectricity. So, okay, if I start very generally by the constraints that are imposed by symmetry on the band structure, then one can say that if I have in my system time reversal symmetry is kept in my system, then the eigenvalues for, let's say, positive momentum with spin up must be the same of the eigenvalues at minus k with spin down. And if I have space inversion symmetry, I have a centrosymmetric symmetry, then if I have the eigenvalues at k and minus k for the same spin channel, they need to be the same. So the combination of these two symmetry, time reversal and inversion symmetry, if my system has both of them, then there cannot be any spin splitting. So all my bands are doubly degenerate. If I break time reversal symmetry, so if I apply a magnetic field or if my system shows a spontaneous magnetic ordering, then I break time reversal symmetry. And if I keep inversion symmetry, then my band structure will be split, right? So this is what we usually expect for a magnetic system. So a band structure which is split for spin up and spin down. However, if I have time reversal symmetry, so there's no long range magnetic order, but I break inversion symmetry, then because of this relation, just the space inversion symmetry is broken. So still I can have a spin splitting, which is k-dependent, so which is shown here. So of course, if I integrate over all the Brillouin zone, there will not be any spin splitting, but locally k by k, there can be a spin splitting in the band structure. And so this is basically what what happens in the Rashba effect. So the Rashba effect is an effect where basically I have my particle moving in an electric field of whatever origin. It can be an applied electric field, it can be a ferroelectric order, and I have my electron moving, an electron with K and its spin S. And so the Rashba, basically the Rashba Hamiltonian is a sort of Zeeman coupling between the spin and the V cross E. And so because of this, let's say, formulation, you see that actually it is linear in K. It's an interaction which is in first order is linear in K. So what the Rashba effect will do to my band structure, if I start from a simple parabolic model, what the Rashba splitting will do is just shifting laterally the band structure. And so you basically have this peculiar band structure, which is typical of the Rashba physics. And so now to our, let's say, contribution to the Rashba physics. So we actually thought that if I have ferroelectric material, so just to recall, a ferroelectric material is a material in which I have a permanent order below a certain critical temperature in polarization. And so it's not only I have this long range order, the other requirement a ferroelectric needs to satisfy is the switchability. So I need to be able to switch by applying an electric field from a positive polarization state to a negative polarization state. And so if I have a ferroelectric material and I have spin-orbit coupling, significant spin-orbit interaction, then by means of the Rashba effect, I can basically get a peculiar effect. So here I'm showing again the Rashba bands in the presence of, let's say, upspin polarization. And in the presence of an electric field, I will have a certain spin texture. So the spin texture here means the expectation value of the spin of the Pauli matrices. And so for every n and k, for every state, I can calculate this spin texture. And what happens in the Rashba physics is such that, for example, my inner band has a spin circulating clockwise, and in the outer band, you see spin circulating counterclockwise.
Silvia,
yes.
May I interrupt for just a second because I think it's an important question. Why are you talking always about Rashba spin-orbit coupling? What's wrong with two other types of spin-orbit coupling? Can they not provide multiferroic effects? I mean, Dresselhausen-Ising coupling.
Sorry, Igor. You mean this Dresselhaus?
Yeah, there are three types: Dresselhaus, Ising, and Rashba. Why are you concentrating on Rashba? Is it not possible at all to get this effect with other couplings?
Yeah. So no, you can have okay. So let's say in I think in let's say in a ferroelectric material, you have a polar system, which means that you have a polar group, right? And so you basically have Rashba. Still, you can have Dresselhaus. So Dresselhaus is something that you can have, for example, even if you break inversion symmetry, but without having a polar axis. So, for example, if you have zinc blend, you have Dresselhaus, but it's non-polar. So let's say you can have a sort of spin splitting there, but you cannot really get this, let's say, net spin polarization. I mean, we can. I don't have slides to.
Yeah, maybe we can discuss that later. I mean, also with the strain, actually, because I think you're referring to the Dresselhaus and the cubic components that they won't have the polar, but with the strain, I believe you can have the polar one. But let's discuss that maybe in the Q&A.
Okay. Dresselhaus. Always people. You're right. I mean, Dresselhaus. Some people mean K cube, but you can have what I mean by Dresselhaus is something that has the breaking of inversion symmetry without having a polar axis, so like Zunger definition or something like this. But yeah, okay. But in general, of course, I mean, any kind of spin-orbit coupling can produce a sort of spin splitting. But I believe this effect, you don't have it in a you need a polar axis, right? It's not enough to break inversion symmetry, but you need a polar axis.
Exactly. But I think with some strength you can do that. Okay.
Right. Yeah, sure. Yeah, so basically, going back to the effect here, I mean, you have a certain spin texture which is bound to the direction of polarization, which implies that if you switch the direction of polarization, also your spin texture will be switched. And so you basically achieve a control of your spin texture, which is non-volatile, because a ferroelectric, if you switch the polarization, it will not go back to normal unpolarized state. It will stay polar, and so it will keep its spin texture. So since one of the dream of spintronic is the electric control of spin degrees of freedom, this sort of could provide a way. And so our materials of choice since, I don't know, 2013 has been germanium telluride. And so in our first proposal, we used it really to show that you have a large Rashba effect, but not only that, the important thing here is that when you switch the direction of polarization, you also switch the spin texture. And then, like 3 years after our proposal, we managed to convince some experimentalists by doing ARPES and spin ARPES. Here, of course, it's a bit complex because in addition to a bulk Rashba effect that you have in germanium telluride, you also have surface Rashba effect. So we have to disentangle, let's say, the two effects, but let's say that the experimental result well match our prediction. And then recently, of course, with Rashba, you can basically achieve, or your dream would be to do spin to charge conversion. And so this is what my colleague in Milan tried to do that with germanium telluride interface with iron. And it seems that you can really sort of control the spin to charge conversion by means of an electric field which is applied to your heater structure. Okay, so I hope this has given you a short overview of what we have done in this field, and hopefully stimulate more work in this Rashba ferroelectrics. So let me go back now to the main topic of the talk. Okay, so I wanted to spend a couple of slides just to introduce the system I'll discuss, and these are basically two-dimensional material. So it's basically one atom or few atoms thick material, and they are held together by van der Waals interaction, weak interaction. And so, I mean, they have nice properties, but probably one of the most important is that because of this weak bonding between the two layers, you can actually stack them as you like. You can really play Lego with 2D material. You can stack a 2D ferroelectric on top of a 2D magnet. You can stack molybdenum sulfide on top of, I don't know, some 2D ferroelectric, whatever you want, you can do without, having to bother about, lattice matching and interdiffusion, which is something we usually have to deal with when dealing with 3D material. So they're very flexible. And 2D material also flexible. So they are very rich. And they are rich, let's say, from the electrical point of view. There are metallic and semiconducting insulating 2D magnet. They are chemically rich. There are chalcogenides, peptides, halides, binaries, ternaries. They're crystallographically rich, triangular, honeycomb lattices of the kinds. And then, of course, from the magnetism point of view, they are also rich. So there's some have magnetization out plane, some have magnetization in plane. There are collinear, non-collinear, non-coplanar. So they are really a good class of material for theorists and also experimentalists to play with. So, okay, there are challenges, of course, in this class of material. Many of them, not all, but many of them, especially the semiconducting one, have low Curie temperature. Many of them are not so stable in air, and they're not yet scalable. But of course, we have theories. So on our side, the most compelling urgency is to understand their behavior a bit better. And so when one speaks about, modeling of 2D magnet, the first thing that comes to our mind is this Wagner theorem, which actually says that if you have your spin are isotropic, so if you have a Heisenberg model, then your 2D magnet will never order. And so to have it order, you need to have some kind of anisotropy. And so this is where spin orbit actually plays an important role. So to achieve a long-range ordering in a 2D magnet, you need to have spin orbit coupling or some kind of anisotropy in the system. Yeah, so mainly the talk will be on nickel halide. So I wanted to introduce a bit the system. So they exist in crystalline form. They are van der Waals crystal. And if I slice one monolayer, I basically see that the arrangement of nickel is on a triangular lattice, and every nickel is surrounded by a cage of octahedral halide, and they are edge sharing. There is a small trigonal compression in the direction perpendicular to the layer, but that's really small. And so nickel is the 8, and I have an octahedral crystal field, so I have the T2G fully filled and the EG half filled. So I have 2 Bohr magnetons in form of nickel atoms. And then if I move from nickel chloride to nickel bromide to nickel iodide, I'll see my spin orbit coupling increases. So I expect larger spin orbit coupling effects in iodide compared to chloride. And so these materials were in bulk form. They were studied back in the 80s, and already at that time by Neutron, I believe, some complex magnetism was detected. And so one of the questions is this complex ordering kept when I move to the monolayer? And so this is why we started basically the analysis of a monolayer of nickel halide. So a couple of ingredients before I get to the results. First ingredient I need is frustration. So frustration in magnetism is what? It is a material in which there are many interactions and the material cannot satisfy all of them. So typical example is an antiferromagnetic coupling on a triangle basically. So what happens is that these two want to be antiferro, but what is this third spin doing? If it lines up, then this interaction is frustrated. If it lies down, this other interaction is frustrated. So the system tries to find a compromise by choosing generally non-collinear and more complex ordering, which however tries to balance all the interactions that are at play in the system. And so the frustration is strongly tied to the lattice. So there are certain lattices that are particularly prone to frustration in two-dimensional. The Kago made a triangular lattice in three-dimensional pyrophores. And so you can also have frustration in a single chain. It's enough, for example, to have a small first nearest neighbor interaction, which can be, ferro or antiferro, but that's small. But if I have a large J2, large second nearest neighbor interaction, which is antiferromagnetic, then it depends on whether the system has a large anisotropy or small anisotropy. If I have a large anisotropy, I have an easing, sort of easing spins, then my ground state will be like up, up, down, down, up, up, down, down spin chain, so that at least the system satisfies the second neighbor interaction. If the system don't have a large anisotropy, then the ground state of this frustrated chain is actually a spin cycloid. So something where the direction of the spin moves from side to side in a certain wavelength. So you expect with frustration to have a complex spin ordering. That's the first ingredient. And so we move to the DFT characterization. And so we map basically our total energy on, for a moment, just a Heisenberg Hamiltonian. And we extracted the first nearest neighbor J, which is strongly ferromagnetic, negligible J2, this is what we obtained for nickel halide, and then a strong antiferromagnetic J3. And so you see that if I now try to place, this interaction on my lattice, then my first neighbor is strongly ferromagnetic. So if I start from the central spin, all my neighbors will want to be up. But already at the third neighbor, I need to have an antiferromagnetic interaction. This is what I get from DFT. But you see that I cannot satisfy again all the interaction at play, because if I place this anti-parallel to this one, then it cannot be parallel to this one, which is what the J1 would tell. So this tells you that already at the Heisenberg level, we expect some non-collinearity. We have some frustration in the system, so we expect some complex spin ordering. Now, second ingredient. So I told you that usually first approximation that physicists do for their spin Hamiltonian is Heisenberg-like. Usually, well, this is not completely true. So the more general approach is having basically a matrix, right? Coupling a spin on site I to a spin on site J. So I can always decompose this 3 by 3 matrix in 3 terms, one which is the trace. This is from the even mathematical point of view. One which is anti-symmetric contribution, and the other one which is the basically traceless symmetric contribution. So if I now look at their physical meaning, so what I have is basically that this first term is the Heisenberg, usually the Heisenberg term. This one, this second anti-symmetric, is what people call Cheleshevsky-Moria interaction. So this is a cross product of the 2 spin. And then we are left with this 3 term, which is something people usually don't calculate, right? It's usually very, very small, but it's there. It's called an isotropic exchange. So this 3 term, what would they try to do? So Heisenberg, of course, depending on the sign, will want the spin to be parallel or anti-parallel, but it's isotropic. So it's the same if the spin are like this or like this. Doesn't care about the direction. The Cheleshevsky-Moria interaction, it's a cross product. So it will want to count the spin, not avoiding them being parallel or anti-parallel. And it has a certain sign. It's a chiral interaction. So the spin want to come, for example, like this and not like this. This anisotropic exchange will actually do what? We'll also tend to align the spin along a certain direction. So people call it sometimes two-side anisotropy. So they want to have a certain direction. So it's not single ion anisotropy, but it's like 2-ion anisotropy, but still favors the alignment of the spin along a certain direction. Yeah, so in our case, okay, Cheleshevsky-Moria and anisotropic exchange are both related to spin-orbit coupling, which means that we expect large effect on heavy atoms and small effects on light atoms. From the, let's say, from the symmetry point of view, it is known that if I have inversion symmetry in my system, I don't have Cheleshevsky-Moria. So Cheleshevsky-Moria is only there when I break inversion symmetry. And in my nickel halide, I do have inversion symmetry, which means that I don't expect any DM interaction here. And due to the space group of this system, basically I can predict the form of the tensor, and it is actually made like this. So there are 3, in principle, different diagonal term and 1 off diagonal term. And I know it's symmetric, so JYZ it's equal to JZY. Okay, so now we estimated this and we did it for the series, right? We started from nickel chloride and then moved to nickel bromide and then to nickel iodide. So what we get from nickel chloride basically is that it's minus 5.1, minus 5.1, minus 5.00 elsewhere, which means that nickel chloride is a pure Heisenberg system. If I increase a bit the spin-orbit coupling, then I start seeing some effects. The 3 diagonal terms get different and also some of diagonal pop. And in nickel iodide, this effect is even larger, much larger. So I have strong off diagonal effects. And so you see that because nickel is always the same, then if I see some differences, then they must come from the spin-orbit coupling of the ion. So they must come from, in particular, iodine. So now DFT, we can do only small system and we can look at t equals 0. So to do approach finite size, finite temperature, and also larger system, we did Monte Carlo, which means that we mapped our, we evaluate the parameter from DFT, then we got our spin Hamiltonian. By means of Monte Carlo, we basically got the spin detection as a function of temperature. Okay, so yeah, just the notation, basically we have three-dimensional spin here, and the way I will show is that I will show by arrow the projection of the spin in the plane, and by color I will show the out-of-plane component. It's just a slide for the notation. Okay, so what do we get for, we now know the parameter. Let's do Monte Carlo and let's see what kind of spin ordering we get. So in nickel bromide, what do we get? You see here, maybe not so clear, but what this tells you is that basically you see some black arrow which change, and also the direction of the out-of-plane component is, not the direction, yeah, the component, the out-of-plane component is moving from side to side, which means that basically we have a helix propagating along this x-axis. So it's a spin helix. So the spin rotates in a plane which is perpendicular to the propagation direction. And so you see here from this spin structure factor that it's actually a helix, right? A wave. And also by means of Monte Carlo, you can estimate the specific heat and extract the Curie temperature. And you see that they are low. This also we expect. Frustrated systems generally have low ordering temperature because they need to satisfy many interactions. So we expected that, and it's also compatible with what people measured for bulk systems. So it's of the order of 10 or 20 Kelvin. And so this we expect, right? We have frustration in a system. We know a spin helix is likely. What we didn't expect was what we got for nickel I2. Because for nickel I2, we got something like this. And so you basically see there is a lattice. It's a complex spin order. And at that time, we were not at all experts, still we are not. But we could recognize that this was a kind of skyrmionic lattice. So I'm sure there are experts in the audience about skyrmions, so I'll be rather fast on this. But skyrmions in general are topological object there are many variants of skyrmion. Also there are anti-skyrmion in which the direction of the spin, let's say the rotation, changes from angle to angle. So for certain symmetry direction you have, I don't know, spin circulating clockwise, and for other direction you have spin circulating counterclockwise. So here also we don't have any continuum approach. We have discrete spins, which means that to calculate what characterizes the skyrmion, this topological charge, we basically had to consider like the formulation of the topological charge on a discrete lattice, or with discrete spins. And so we basically evaluated on this triangle, like this triple scalar product. So a scalar, what is called scalar spin chirality. So you see here that it's a so it's a scalar product with a cross product of two other. And so you see already from here that to have a non-zero, finite topological contribution, you not only need non-collinearity, but you need non-coplanarity. So it's not enough to have a helix. You need to have something that's deviating from the plane. What I would like to outline is that most of the skyrmionic system actually have a phase diagram which looks like this. So it starts from something that it's frustrated, and then there is a region where skyrmion appears. So usually you see skyrmion upon application of a magnetic field. You don't have skyrmion as ground state. This is what generally happens. But in our case, we do, right? This is what we get. And also we don't have, let's say, bare skyrmion. We have anti-skyrmion with topological charge Q equal 2. And so we could basically, via always Monte Carlo simulation, we could estimate again the Curie temperature here by calculating this as order parameters is topological charge per magnetic unit cell. And so here we have a topological state without magnetic field. It's a lattice. It's not single isolated skyrmion. And when we discovered it back in 2020, it was the first example that we knew about topological anti-skyrmion into the magnet. And it's not driven by Zeruski-Moria, right? Because the M is not there. And so we also thought it's interesting to look at what happens under magnetic field, because usually the skyrmion pop up with magnetic field. And what happens in our case is that basically this anti-skyrmion, let's say, disappear and evolve more into like standard skyrmion, like Q equal 1, topological charge equal to 1. So basically, what happens is that if you don't have any magnetic field, you have this topological charge equal to 2, then there is a sharp transition to state Q equal 1. And then if you apply a really large field, okay, here you shouldn't look at quantitative, Tesla here. It's probably far off from the reality because of that computational parameter, but the sequence of transition should be correct. So we start from Q equal 2, then jump to Q equal 1, jump to ferromagnetic state. Okay, yeah, so we wanted to understand a bit more why we get this. And so, okay, we have a symmetric matrix, right? Which means that we can diagonalize it always and get the eigenvalues and eigenvectors. And so we looked at the eigenvectors and we basically observe that, for example, if we take what we call a plaquette, so a system of 4 atoms, which is like nickel, iodine, nickel, iodine. So these are arranged like this in the nickel iodine monolayer. And so with respect to this plaquette, basically the eigenvector are pointing, let's say, along roughly along the iodine direction, nickel direction, and the one which is perpendicular. And so basically the larger eigenvalues we get is basically perpendicular to the nickel iodine plaquette. And since they are arranged basically in a non-collinear fashion, we believe that this interaction is actually driving, or it's very instrumental to the kind of non-collinearity and non-coplanarity that we actually see. Yeah. Okay. Yeah. Okay. So I should say, actually, that the mechanism is there. We believe that if you have a large anisotropic exchange, then you can really have this anti-skyrmion. What I cannot say is that actually nickel I2 is a system where you really have this as a ground state. Because, for example, if we evaluate the energy of this anti-skyrmion, and also we evaluate the energy of a spin helix, they are basically degenerate. So I cannot, by DFT, we cannot really distinguish between them. So my message would be more about the mechanism than about its realization in nickel I2. But what I believe it's correct and can be said is that anisotropic exchange in this kind of lattices and kind of monolayer in which you have heavy ligands like iodine, you can have a sort of non-coplanarity driven by anisotropic exchange. And as you will see in the rest of the talk, most likely this is the ground state and not this one. And so let me move to the final part of the talk, multiferroicity. So I would like to recall the hype on multiferroics that was a class of material that was very popular in the, I don't know, year 2003 or let's say first decade of 2000, year 2000. And so basically what drove a big attention to this class of material is the discovery that actually if you have a spin spiral breaks inversion symmetry. And so if you make the reverse, so if you have not a left-handed spiral, but a right-handed spiral, then they break inversion symmetry, they drive ferroelectric polarization, and if you switch the handedness, also the direction of polarization will switch. So you have a polarization, ferroelectric polarization with spin cycle left-handed and opposite if you switch the chirality. And this was well proved in 3D system, mainly manganites, oxide, correlated material. So it was very clear that you have electric polarization below the magnetic ordering temperature. So the connection between magnetism and ferroelectricity could not be doubted. And this, of course, was source of nice physics and a lot of attention from the scientific community. So we asked, thanks to a very fruitful collaboration with Riccardo Comin at MIT, we basically wanted to see if we can have multiferroicity, and also multiferroicity persisting down to the monolayer limit. So we explored basically whether this nickel I2, where we know if there's a spin helix, there's complex magnetism, whether this would also be polar. And so what Riccardo and colleagues did was basically they took the crystal and then they exfoliated the layers. And they did also a few layers, 4 and 3 and 2 and 1 layer. And then they did like nonlinear optics. So they did like, I don't know, second harmonic generation and linear dichroism. And they basically measured this 1 layer, 2 layer, 3 layer, 4 layer. And so what you see here is basically that you have a signal which pops up below, I don't know, 40 Kelvin, what seems to be an ordering temperature is actually decreasing if I reduce the number of layers. But even for a monolayer, I have a clear signal. What is important for our purposes is that actually they did a symmetry analysis on their measurement. And they can actually tell us that, okay, second harmonic generation tells us that the inversion symmetry is broken, which means I need to have a magnetic ordering which breaks inversion symmetry. And also the combination of this, the symmetry analysis for the two second harmonic generation linear dichroism also told us that you have a C2 symmetry. So usually you have a threefold symmetry, a triangle lattice. But here, you reduce it and you have a C2. So this is well compatible with the spin helix. And so we thought, okay, maybe a spin helix has a ferroelectric polarization. And so, we thought, okay, let's maybe calculate the spin helix and whether it has a ferroelectric polarization. But of course, we know since long time that there is a basic mechanism to explain polarization driven by complex spin. And this is due to Katsura, Nagaosa-Palaski, also Mostovoy picture. So what it says basically is that if you have a non-collinear spin texture, so you have, for example, a spin 1 and spin 2 with different direction, then they give rise to a dipole, and one can write the dipole in the following way. So it's a cross product of the two times the cross product with the propagation vector. So you have a cycloid like this, what you have in terbium manganite, a cycloid like this with polarization pointing up. But this also tells us that if you have a spin helix, this bare KLD mechanism wouldn't give any polarization, right? Because it's perpendicular, right? P is predicted to be 0 because it's perpendicular to the cross product of S1 and S2 times the propagation vector. So we wouldn't expect any P from this bare model. But we thought we could extend it, and this was actually done not by us, but far back in 2011 by Shang. So what he and co-authors wrote was that actually you can still think that you have a contribution to polarization by the cross product of two spin times not just basically the propagating vector, but times a matrix, which you can call like a magnetoelectric tensor. So of course, this K and B simple model is like a reduction. This is more general framework. And if you have your K and B model valid, then your tensor has a specific form with just one independent parameter. And so with DFT, we estimated this. And so what we got, it was actually that many elements were different from 0. And so we have, of course, small number. Well, this is in 10 to the minus electron per angstrom, which is difficult unit, but let's say, I mean, if you have like barium titanate, which has like 30 microcoulomb per centimeter squared, here polarization is the order of magnitude smaller. So you expect to have polarization induced by spin order to be small, and this is also actually what you get here. But it is intriguing that you have some kind of polarization below, again, the magnetic ordering temperature. And so by means, again, of Monte Carlo simulation, we did the spin helix, and then on top of each spin, we basically, or spin couple, we basically built our contribution to polarization, sum up over the whole lattice, and basically get a net polarization along X, which is basically perpendicular to the plane in which the spin rotates. The other component are 0, and it's peaked exactly at the same Curie temperature. So you basically have that ferroelectricity pops up below the magnetic ordering temperature. So let me come to the conclusion. So I told you that you can play Lego with 2D material, and you can stack graphene, and you can stack on ferromagnet and ferroelectric. And then now we also have a multiferroic brick that we can play with. And with this, I would like to close the talk, and thank you for your attention.
Thank you very, very much. This was really very, very good, and also very broad spectrum of all the things you've covered, actually. And I've learned a few new things. So now it's open for questions. So maybe I think, Musa, let me bring you up to the panelists. I'm not sure if you had a question, but please raise your hands if you would like to ask a question directly. And I will bring you up to the panelist groups. And I think, hang on a second, in the Q&A we have already, we get Chris. So Weida Wu, can you ask your question perhaps?
Hi, can you hear me?
Yeah, we can hear you.
Yes.
Okay, great. Thanks. Thanks for the very nice talk, Silvia. I'd like to ask the question about the very last point. This you calculate this have a multiferroic property, meaning you also have a magnetic ordered induced ferroelectricity, right? So is this only for the 2D thin film, or this calculation can be extended to bulk? In other words, whether the bulk
they can. we did everything for the monolayer. We didn't do for the bulk, but actually you can, of course. So here the way it was done was actually really taking two spins, counting them, and calculating the contribution of these two spins. In bulk, what you can do is setting up the spin helix, and also from layer to layer, depending on, usually I think you have an antiferromagnetic coupling between layer to layer, and then you can calculate the bulk polarization, the overall the units. But yeah, it can be done. It can be done for sure.
Or is it known? I'm sorry to ask.
Yeah, I think for nickel bromide there were some. I think to measure it, to switch it, to do the field and do, I don't know, piezo force microscopy, or it's very hard. Also, in our case, I think Riccardo Comín and other tried, of course, to contact and switch, which would also be the most the really smoking gun of ferroelectricity, but that is very hard to contact a monolayer. So it's really hard. But with this symmetry analysis, you can, let's say, see where the symmetry is reduced, along which direction you have symmetry reduction. So you can basically have sort of indirect but still strong proof that ferroelectricity is there. But I don't believe that yet, for example, the quantification of polarization is available in the literature.
Yeah. Let's go
Thank
next
you.
to Krishna. Krishna, can you unmute yourself and ask your question, or should I read it for you? You wrote it down, but I'm not sure if you have. Go ahead.
You can read it.
No, you go ahead. Go ahead. No, we are here now. Go ahead.
Okay, thanks for a nice talk. I have just like I'm doing something in two-dimensional van der Waals material. So can we do with this interlayer coupling in two-dimensional van der Waals material? So how can we calculate with your system like the interlayer coupling and stability of the ferromagnetic phase?
Sorry, I'm not sure I got your question. So
So my question is, can interlayer coupling in two-dimensional van der Waals material plays a vital role? How can we say stability in ferromagnetic phase in monolayer or bilayer system with interlayer exchange? Another query is that if stacking of the lattice point between the layers, then how it changes the critical temperature? So how anyone can calculate these kind of physical properties with your system?
Right. Okay. So to the question of interlayer coupling, of course, you can't do that with DFT. We did it. Of course, you have some certain approximation because van der Waals are not correctly treated. But we sort of, we have some argument to say that this is much stronger than what we expect. So of course it's van der Waals. So we expected, micro EV, right, the interaction. And it's not like this. Because of this iodine 5p states, they are far extended in the van der Waals gap. So there is really a strong interlayer coupling. And so this also, we have, you can read the paper. I don't think I have a slide to show you right now, but in this Nature paper, we basically reported how the Curie temperature depends on the number of layers. And so this, of course, it decreases, but still, even in the monolayer, it's ordering is there. What we didn't address was the stacking. So this, we just did the like experimentally known stacking, and we didn't try to change it. So this I don't have, but it can be done, of course, just we didn't do it.
Okay.
Actually, now these days,
let's go on. So, Krishna, if you don't mind, we're going to move to another question, and then maybe if we have time, we come back to you. Okay? Because there's quite a few people that would like to ask question. So, Jose, can you unmute yourself and ask your question, please?
Yes, thank you very much, Silvia, for a very nice talk. You mentioned that the spiral and the skyrmion lattice are degenerate. Is this a property of the model? I mean, some symmetry, some hidden symmetry, which makes them degenerate, or is just something that is due to the particular parameters you were looking at?
Yeah, I would say it's due. I mean, it's the result of the calculation. We cannot. I mean, ab initio, we cannot cheat. Right?
You can cheat a lot in ab initio. I take that. I would take that back. But you don't cheat. But some people can cheat.
Let's say we have a bit of flexibility. I think, for example, if we change the U, then we might get different results. But what we also thought that actually this anti-skyrmion, it's I believe people call it like a 3Q state. So you basically have three spin helices merging. So it's not completely unrealistic that we get very comparable energy between a spin helix and 3 spin helices. This was our explanation.
It will depend on how these helix interact, if they have an attractive or a repulsive interaction, essentially. But this you cannot determine from DFT, I guess. It's
well, we
calculated, but I don't think not from the symmetry.
Right? Yeah, we didn't address it. Just we thought, okay, we thought it's realistic to they have the same energy, but we didn't really focus on the interaction. Let's say. But I guess it can be done, of course. Just
okay. So let's go next to Celia Rogelio. If you don't mind.
Thank you very much. Can you hear me? Yeah. I have we have a question regarding in the presentation you concentrate on nickel D halides, and is there any reason why you didn't change to the metal like iron or cobalt?
I was tempted. I have slides to show you. Okay, let's see. Can I steal like 2 minutes more? Let's see if because I mean we did.
Your time. Now it's your time. It's okay.
Just let me get here. So okay, let's say we did semiconductor. I wanted a semiconductor. I was afraid of doing, let's say, partly filled shell. So because then you have Jan Teller and it's of course interesting, but it's more difficult to say. So we just look at D3, D5, and D8. And so basically, because I thought, okay, well, we have this anisotropic exchange because of iodine, and I thought that we would always have for iodine a large anisotropic exchange, but we didn't. Actually, and also, okay, here I think we, in collaboration with the group of Roser Valenti, we basically made a characterization, and also basically, there's not much more I would say than applying Budan-Afkana-Mori rules, extend to complex spin to interpret, let's say, the sign of the J related to the bond, to the filling and the orbital that have a larger role in hopping. And so basically the conclusion is, let me jump to the conclusion. You can, I think I have a, let's see. I should have a reference here somewhere. Yeah, okay. It's a paper, it's a P3P paper in this year. But basically the conclusion is that in vanadium, you don't have this strong Kita-Efter. So here it's not in our basis A, B star C, it's in the usual, Kita-Efter basis with this bond dependent setting. And so you see it's not what I reported previously, but basically you should look, this is the Heisenberg term, and in this case this Kitaev term, and you see vanadium is small, even for iodine is small. And vanadium is also antiferromagnetic, which might be interesting to study because it's probably like a spiral, but you see it's small, and it's small. Yeah, in the paper we explain basically why it is small, and we conclude that actually it's because of the 8, and it's because of the EG hopping that makes the big contribution to exchange. Here you don't have any EG, of course, because it's P3, just T2G in the majority shell is filled, and so you don't have an anisotropic exchange. Also, manganese is a small, very small exchange in general, and no anisotropic exchange. So the 8 is really crucial. So maybe one should explore other D8 system to have a sort of large anisotropic exchange. So what I believe is a really typical characteristic of nickel I2 is that it has this strong anisotropic exchange at first nearest neighbor, but it also has a strong antiferromagnetic J3, which also frustrates this lattice. So it's not only an isotropic exchange, also the J3 is well, like instrumental to getting this complex anisotropic spin texture. So yeah, the answer is we tried, but we failed. So just the 8 seems to have a large anisotropic exchange. The other we tried are small. Maybe iron or cobalt have larger anisotropic exchange, but we didn't look at it because they have additional effect that one should consider.
Perfect. Let's go to Elia and then Patrick, but first Elia, that has been waiting a bit. Go ahead.
Hi, Silvia.
Hi.
Very nice talk. Thank you for the presentation. I had another question regarding these multi-layer structures. So you show in your slide that you can change the Curie temperature according to the number of layers you have in your van der Waals material. But do you have also some information about the spin texture you can have at the surface? So does also the spin texture change as a function of the multi-layer or not?
Yeah, good, very good question, but we didn't do it just for not from the, let's say, from the theory side, we really did Monte Carlo in just one layer, monolayer. In principle, it could be done in 2 layers, but we didn't do it. But that's a very good question. Yeah, interesting, but yeah, I don't have an answer for the moment.
It's too difficult for the moment.
Yeah.
But she will have later.
Yeah. Well, it's interesting, right, to see, the dependence, because this strong frustration, as I said, the interlayer coupling is strong, right? It's strong, and it could also be probably, maybe there are some non-Heisenberg terms in there, who knows, just we didn't address.
Okay.
Thank you.
Patrick, can you go ahead and ask your question, please?
Yes, hi there. Can you hear me?
Yes.
Yes, thank you. Thank you very much for a very nice talk. A simple experimentalist question. For the spin textures that you showed, in particular the skyrmion lattice and the spin helix, could you indicate what are the relevant periodicities? I mean, how large are they?
Oh, yes, that's a good, yes, I forgot to mention, that's a very important, yeah. Okay, so let's say, here maybe, yeah. So, okay, well, I should say that, of course, with Monte Carlo, I cannot make any incommensurate. I cannot treat any incommensurate helices, right? So if it's incommensurate, I don't know. Whether it's incommensurate or commensurate, I cannot say, because we commensurate it, let's say. From our, let's say, force commensuration, we can say that it's probably 8 times 8. What we could estimate here is like 8 times 8. So it's rather small, right? So this is the unit cell, and you have 3 skyrmions in this 8 times 8. So it's like, yeah, small object, right? Because they really, I mean, rotate from side to side by a lot. Yeah, so this was also one of the, I don't know, we asked to the experimentalists also if they could, you know, probe this, but since they are so small, I don't know if it is
looks
that easy. So they look to be really small.
Yeah.
So
And the same
from
for the
what I
helix,
can say,
guess.
it's probably 8 times 8.
All right, thanks.
Yeah, you're welcome.
Okay, so Igor, go ahead.
Hi. Thanks, Silvia. Interesting talk brings many thoughts. I don't want to be very controversial, but I think you have tendency to make general statement in cases when the statement is applicable only for a particular case when you are discussing. For instance, there are van der Waals material where TC actually increases with a small number of layers compared to the bulk. Chromium S boron, the large J3 is extremely ubiquitous for all triangular materials, and usually does not come from ligand-ligand interaction, but from T to G, e.g. T to G hopping, and so on. But I want to actually ask question, and that's going back to Jose's question about nickel diiodine. As we established, there is no symmetry reason for these two configuration to be degenerate, but it's exact analogy of, for instance, triple spin density wave in niobium diselenide, where the energy difference between a single charge density wave and 3 overlapping charge wave, it's computable but extremely small. So the same thing is true here, but in that connection, but it's parametric. So did you try, for instance, varying U, or did you try to turn off spin orbit coupling on iodine? Because obviously there is no spin orbit coupling on nickel, it has closed shell, so everything comes from iodine. And that should help you to actually pinpoint what particular type of interaction creates this, because helix can be created by isotropic interaction by itself. Maybe interaction between helix is spin orbit derived, and so on.
Yes,
so did you try to vary parametric?
Yeah, we changed. I remember we changed the U, and what we could, let's say, infer was that, of course, the absolute values of the J, J1, and J3 they do change. What we convinced ourselves about is that the ratio doesn't change so much. So, for example, the off diagonal to diagonal pretty much stays there. So let's say that this is why we didn't worry so much about, you know, the physics. That
let's say, what if you turn off spin orbit coupling?
Spin orbit coupling, you mean just on iodine or complete spin orbit coupling?
Well, I mean, it should only matter on iodine. I don't think.
Right. Yeah. So of course, I mean, anisotropic exchange is not any longer there.
Right.
And so
but do you still get helix?
Do
you still get helix or not?
We do get a helix. The helix comes from J3, right? Because
They
J3
can come from
is
J3,
antiferromagnetic.
right? Right.
So,
And
yeah.
what about the degeneracy? Is degeneracy still there?
Right, I'm not sure we did it.
Okay,
I don't think you can get an anti-skyrmion if you don't have so of course if you kill spin orbit coupling and isotropic exchange is 0, so you're basically left with the Heisenberg.
That's right. So basically I'm aiming at establishing whether this skyrmions is really a relativistic effect, or maybe I agree that it's less likely, but it's not impossible, pure frustration effect.
Right, yeah, okay, this, as I said, for example, I think we tried at some, I thought, okay, well, anisotropic exchange is really instrumental. So I think we killed J3, and then we didn't get the skyrmion, the anti-skyrmion. So this is why I say that both, so the system needs to be frustrated in the background, let's say. So I need this J3 over J1 as main ingredient. And then on top of this, if I have this non-coplanarity, then I get the anti-skyrmion. This is what I would say I learned. So that I need a frustrated system, and so this would have a helix, right? But then I need some non-coplanarity, right? And the non-coplanarity comes from an isotropic exchange. But if I only have an isotropic exchange, then I don't get the anti-skyrmion. At least in the trials we made with sort of realistic parameter. Maybe if you have it very large, maybe you do, but it's not in a realistic range.
Okay, it's opposite to what I was asking, but never mind. I was asking what happens if you turn off spin orbit coupling.
But
then just keep the frustration.
You don't have an isotropic.
But keep frustration. Right? But keep frustration. Can you
keep
get
frustration? You get a helix. You get a helix, right? You have only have J3 over J1, and this.
But you don't get triple helix.
No, I don't think so.
Okay.
I don't think so.
The electrons don't know left from right. You know, the spins don't know left from right without that. That's the problem.
But I can dig out better, but yeah.
So, okay, I'm going to stop the streaming now. Just so we can now, by the way,